My name is Matt Knight. This is Marc Newlin. We're from Bastille. For the next hour or so, we're going to be talking about some of our favorite techniques and methods for reverse engineering wireless signals. It's kind of our primer on wireless reverse engineering. So Marc Newlin here is a security researcher with Bastille. You may know him from discovering the mousejack vulnerability in 2016, which is a series of pretty scary wireless keyboard and mouse exploits. And Marc has kind of a non-traditional path into software-defined radio and wireless reverse engineering. He got into it by way of being an individual entrant to a number of DARPA challenges, in which he came in second and third, I believe. So that's Marc.
And this is Matt Knight. Matt and I work together on the threat research team at Bastille Networks. Matt comes from a more traditional educational background, having earned a bachelor's in EE from Dartmouth College. You may have seen some of Matt's work at DEF CON or CCC last year. He did a project of reverse engineering the physical layer of the LoRa wireless protocol, which was some pretty cool stuff. Matt's just an all-around badass embedded and wireless security researcher.
All right, so just a quick intro here. Since we're here at Hack in the Box Technical Conference, we're going to assume that most people in the room are comfortable with dealing with binary data formats, whether it's network traffic or malware reversing. You know, if you've got a bunch of ones and zeros, you're going to be comfortable looking at it and figuring out what's there. What we're not going to assume is any real radio or DSP domain knowledge. We're going to rely on tools and techniques to get around all that stuff. So you're going to be able to apply your traditional software and network chops to the wireless domain to reverse engineer these systems. So why is this relevant? Well, it's 2017. Wireless systems are everywhere. That's being driven by the growth of mobile and the Internet of Things. We have fewer and fewer wires connecting these devices and more devices every year. Now, regarding the Internet of Things, apart from being everybody's favorite buzzword, we all know, since we're working technology, we all know that this is really just code word, marketing speak for connected embedded devices. And these quote-unquote smart devices are usually pretty dumb. It's been shown over and over again. And there's good reason for it, and that's because embedded systems are built on compromise. There are some real kind of hard truths that they have to make trade-offs between in order to perform optimally. So for instance, embedded hardware is often under a lot of size and cost pressure. Maybe it has to fit into a small package, like it's a wearable device or something like that, or it's being produced in mass market, so it has to be cheap. It might be battery powered, which would limit the type of computation you can do on it. It may be deployed in challenging environments. It might be mounted on a telephone pole or outside somewhere hard to reach. Maybe it's put in the basement of somebody's house and is left there for 20 years. So you have lots of legacy problems. Related to that, embedded systems can be very difficult to patch as well. They may have one-time programmable firmware, which you physically cannot rewrite, or they may have limited network access to push firmware to them. So one could say that these embedded systems are really vulnerable by virtue of the constraints placed on them. So this is manifested in a series of fairly high-profile attacks in the last couple of years, and I'm just going to intro two of them to illustrate why this domain is important. And specifically, these are wireless attacks on embedded systems. The first was a series of vulnerabilities facing home alarm systems that was discovered by our colleague Logan Lamb in 2014. And Logan analyzed the legacy RF link that connects the wireless sensors that you place on your doors and windows around your home, that connects those sensors back to the home alarm system state monitoring panel that triggers alarm conditions and calls the police when somebody breaks into your house. And the people that designed this system designed a one-way unencrypted link with no replay protection and limited anti-jamming mitigation. And they did so to make it very legacy compliant and inexpensive. Also so that you wouldn't have to replace the batteries on these sensors often, like once every 5 years or something. So they had some design features that they were trying to build in, but in the process they traded on security. So Logan found that he was able to jam these signals with impunity so that alarms didn't get reported. He could inject commands to trigger false alarms maliciously, and he could also eavesdrop on signals within other people's homes to do some like spooky SIGINT type things, track people as they're moving throughout their house and stuff. And again, he was able to do all this by virtue of the fact that the system was not designed with security in mind. It was designed with some more UX aspects instead. So he was able to compromise that. The second vulnerability I'll talk about briefly is the mousejack vulnerability that Marc discovered in 2015. And Marc analyzed the RF link that connects non-Bluetooth wireless mice and keyboards to the dongles which you plug into the computer. Now, I say non-Bluetooth because they use a PHY that's made by a company called Nordic Semiconductor. The physical layer is very similar to Bluetooth, but it doesn't have any of the MAC layer networking or security protections on top. As a result, it has better battery life and is less expensive, but obviously you don't have those features built into the protocol. It's left up to the manufacturer to implement those things on top. So by analyzing these proprietary links, Marc was able to find command injection and keystroke sniffing across virtually all the devices that he looked at had some form of this vulnerability. So again, it's another example of embedded constraints leading to vulnerabilities in action here.
So at the IoT Village at DEF CON last year, Matt and I gave a talk on reverse engineering a toy drone. And as part of this talk, we had a section where we discussed some RF fundamentals and kind of touched on our wireless reverse engineering methodology. And we got some good feedback from this. And what we learned is that there's a lot of interest in applying software-defined radio to these type of security problems, but people tend to find the RF intimidating, maybe think it's too academic. But Matt and I are evidence that this really isn't the case. So I have no college background, Matt has a bachelor's degree, yet we've both been able to do pretty meaningful work in the wireless space. And so the thesis is that no PhD is no problem. So we're going to start by discussing some of the common hardware and software tools we like to use. We're then going to provide a short crash course in the bare minimum wireless fundamentals, RF fundamentals that you need to understand. We're then going to introduce a RF engineering workflow that can be applied to reverse engineer any wireless system. And this is really the key, that you can take this same workflow, the same process, and apply it to any wireless device to reverse engineer it. We're then going to demonstrate this workflow by reverse engineering a few different wireless devices. And we're not going to get into any DSP topics. The reason is that you really don't have to have any understanding of the underlying math to use this stuff. So when you're getting into wireless hacking, you're probably wondering, what is the barrier to entry and what hardware and software do I need? And conveniently, there's a great open source ecosystem around this. So it used to be that software-defined radios were really expensive lab equipment, but now it's been commoditized, and so really on a hobby budget, you can get software-defined radio hardware and do work in the space. So on the radio side, we have the distinction between hardware-defined radio and software-defined radio. So a hardware-defined radio would be something like the cellular modem in your phone or the Bluetooth radio in your laptop. And it's an integrated circuit which is designed to do one protocol really well, but it's not good for a lot of reverse engineering processes because you can't configure it in the way that you need to look at an unknown protocol. So we have some devices here for looking at Bluetooth and Nordic NRF24 and sub-gigahertz FSK protocols and Zigbee 802.15.4. Then on the software-defined radio side, the big difference between a SDR and HDR is that an SDR can be reconfigured on the fly. So you can tune it to different center frequencies, you can set different channel bandwidths, and instead of the logic that makes it a Wi-Fi radio or a Bluetooth radio living on the hardware sends the raw radio data to your host computer or an FPGA, and then the logic that makes it operate on a specific protocol lives in software. And so because of this, you can iterate on it quickly, and as you're reverse engineering a protocol, you can change the behavior of the radio on the fly as you learn more about the device you're looking at. On the software side, there's GNU Radio. This is a DSP suite, really great open source software. This has blocks which abstract away all of the different signal processing things you need to do. So you can use a tool called GNU Radio Companion and drag and drop these blocks together to build a flow graph that does all this magic radio stuff and turns radio waves into bits and bytes that you can operate on disk. At Bastille, we've contributed a couple of GNU radio modules. Matt built the GR LoRa module, which is a transceiver for the LoRa LPWAN protocol. I released GR Nordic, which is a transceiver for the Nordic NRF24 devices. And the nice thing here is that because a lot of really smart people have built up this ecosystem, you can leverage it very heavily and not have to understand any of the radio stuff and just treat this as a regular binary reversing problem.
All right, so with the exposition done, we're going to dive into some technical details here. And what we're going to do with this next section is provide just enough fundamental understanding of exactly what radios are and how they work so that we can frame the rest of the conversation around these concepts. And originally wanted to call this the obscenely short radio crash course, but my colleagues have told me that wasn't profound enough. So instead, we're going to cover these details in kind of at a very high level, provide just the information we need to understand the rest of the content, but really just scratch the surface. So let's get going then. So when we talk about reverse engineering wireless systems, we're talking about reverse engineering the physical layer. And this is the lowest layer in the communication model. And in wired protocols, it refers to voltage, timing, and wiring that defines what is a 1 and what is a 0 in physics, in the physical world. And in electrical characteristics, that is. And in wireless, instead, that refers to patterns of energy that are being sent over an RF medium. Now, RF stands for radio frequency, and it's the electromagnetic waves and energy that are just around us kind of all the time. And if you've ever met Tom Rondo, who's the former GNU Radio project lead, he's been known to proclaim that RF is one of the 4 fundamental forces of the universe, and as radio engineers, we get to play with it. So it's cool stuff. We can visualize what's happening in the RF domain by putting together a picture like this, which is called a spectrogram, or a waterfall plot. Basically, we have time in the y-axis, frequency in the x-axis, and then power in the z-axis, the intensity. So it's a way of visualizing what frequencies are present in the RF environment at any given moment. And we're going to look at a few pictures like that, so just get familiar with it, because we'll keep coming back to them. So you can manipulate RF by using a device called a radio. And as Marc mentioned, radios can either be hardware-defined, as is the case with the LoRa radio shown on top there, or they can be software-defined. And with the hardware-defined radio, again, the features are baked into silicon and are not flexible. With hardware-defined radio, it's really just a way of grabbing raw radio information and passing it off to some sort of reprogrammable logic, whether it's software on a host or configuration of an FPGA. So if you put these elements together coherently, you can come up with a PHY, and the core component of the PHY is this algorithm called the modulation. The modulation is simply just a function that maps how your digital values, your 1s and 0s, get mapped into RF energy. So there are 3 primary properties that can be modulated. You can modulate the amplitude of a signal, the frequency of a signal, and the phase. Amplitude is simply the power. Frequency is the rate at which the periodic signal is oscillating, because all signals are periodic. Phase refers to the offset within a period at which the signal starts. And of course, you can put together some combination of these to make more complex PHYs that have some advantages, but really it all boils down to these 3 elements kind of working in concert with one another. Now, modulators can modulate either analog or digital information, but for the duration of the talk, we're going to be talking about digital modulation modes. And what comes next is the most important concept with all this. If you take anything away from this section, just get familiar with this. And that's this concept of the symbol. And the symbol is essentially a discretely sampled RF state that represents some quantity of information, right? So when you hear the term symbol, just think it's something happening in RF that means either a 1 or a 0. And we can illustrate that by looking at 2 common IoT PHYs. We'll look at frequency shift keying and amplitude shift keying. So FSK is on top. And essentially what's happening is the RF is alternating between 2 frequencies to signify digital values. Now, to contrast that with ASK, amplitude shift keying, instead it's changes in RF power that signifies what's a 1 and what's a 0. So up top we have 2 frequencies, and in this case a symbol is the signal dwelling on one of those frequencies for a discrete sampling period. On the bottom, with amplitude shift keying, we only have 1 frequency, and instead the symbol is denoted by whether or not the signal is on or off. So you're measuring amplitude rather than frequency. So in both cases, the symbol is simply an RF state, whether it's denoted by frequency or amplitude, at a discretely sampled interval that denotes a 1 or a 0, a digital value. We'll keep coming back to this and illustrating this as we go through, but this is really the most important concept to take away from this. Now, as I mentioned, IoT PHYs can get more complicated. You have the notion of spread spectrum, where data gets encoded at a higher rate, which causes it to occupy more spectrum, but also makes the signal much more resilient to RF noise and interference. So 2 examples of this are 802.15.4. There's a 802.15.4 packet on top there, which uses a modulation called direct sequence spread spectrum. And then on the bottom we have a picture of a LoRa capture, a LoRa packet. And LoRa uses a spread spectrum modulation called chirp spread spectrum. Now radios can have 2 functions. They can either transmit or receive. But if a radio can do both, it's called a transceiver. And when it comes to reverse engineering radios and wireless protocols, our main objective is to figure out how the modulation works. That is really how the data gets mapped into symbols. So reverse engineering comes down to doing the inverse of that process, building receivers. So coming up with the opposite of that, or coming up with a demodulator, the inverse of that modulation operation. So that wraps up the background. Who feels confident? Who's an expert? Okay, notice I'm not raising my hand. This stuff is really hard. We went through it at just a high level, covered some core concepts, and we're going to illustrate them in just a minute by walking through 3 examples of some protocols that we've looked at. But in order to frame that, we're going to introduce this wireless reverse engineering methodology that we believe can provide structure and process to reverse engineering these different wireless signals. So before we get into it, I just want to put this picture up and engage the audience for a moment. So this is a spectrogram. It's a capture of a signal, and I'm just going to throw it out to you and ask you to make some observations about what you see. So can I ask for a volunteer to perhaps make an observation about this signal? Yeah, so it is an FSK signal here, and we know that because there are there's more than one frequency represented here. That's correct. Anything else? It is 2 FSK. There are 2 frequencies represented. How about the rate of the state change? Does it look like it's a fairly consistent period, or does it look somewhat arbitrary? So I'll actually argue the opposite. So the signal does change somewhat, but the rate at which it changes, can be divided up into nice, neatly consistent sampling periods. Does that make sense? Okay. And how about can we segment this up at all? Does anything change in time as the signal goes on? So yes, in the front row, basically, we can see up top, the symbol period is a little bit longer, and it essentially we have this consistent oscillating back and forth, where it goes from the lower frequency to the upper frequency to the lower frequency to the upper frequency, and so on, always following the same pattern, right? But then about halfway down, we can see the rate increases a little bit, and then we get some randomness in there, right? So what we can see is that there are really 2 segments to this signal, right? We have some sort of a preamble at the beginning, just some periodic pattern, and then about halfway through, something changes in the signal, right? So what's actually happening is up top we have the preamble, and then once we get about halfway down, we get into the modulated data, and we'll talk more about this in a moment. But we kind of just talked through all the core concepts that we're going to need to reverse engineer these systems, right? So let's formalize this and start to put it into a process that we can apply to these signals. So step 1 to reverse engineering a wireless signal is to characterize its channel. And that's basically find out where within the spectrum the signal lives. So there are really 3 things we're looking for with this. We're looking for what is its center frequency, what is the middle of the channel. We're looking to establish how wide the channel is, how much spectrum does the signal traverse. And finally, we're looking to establish whether or not it's a static channel or whether there are multiple channels and the signal hops around. So those are really the 3 things that come to defining the channel. Step 2 is to identify the modulation. And again, the modulation is the algorithm that defines how your data, your digital ones and zeros, get mapped into RF energy. And this is by far the scariest and most intimidating part of all of this, right? Until you realize that when it comes to these low complexity IoT protocols, you're really just going to be seeing variations on a theme over and over again. There are really just a couple modulations that get applied in different ways that connect 90% of IoT devices. And there are 2 ways you can identify it. If you do this enough, you will develop intuition so that looking at a spectrogram, you can tell what it is. But until that happens, we're going to be able to lean very heavily on open source intelligence and open source documentation to just do this part for us. So we can, leverage public information to not have to worry about blindly identifying modulations based on a spectrogram. And we'll go through this in a moment. Step 3 is to determine the symbol rate. And we can find this through, and again, the symbol rate is how often the symbol state changes to represent data in the phi. And we can identify this through open source intelligence and documentation, but for where it's not present, there are a number of open source tools that we can use to measure the symbol rate empirically. Step 4 is to synchronize against our packet. So we're going to write some software that will essentially identify the preamble and the start of frame delimiter. And these are the two elements that we just talked about with that interactive example that denote, first of all, they're present in just about every digital communication scheme, wireless digital communication scheme that's out there. Essentially, the preamble is a pattern that the transmitter sends out to tell the receiver that data is soon to follow. It also helps with clock recovery. We'll talk about that briefly later, but really the preamble just says, I'm about to send a packet. And then immediately following the preamble is this synchronization feature called the start of frame delimiter. And the start of frame delimiter is a static value that is distinct from the preamble that basically tells the receiver that the preamble is over and what follows immediately thereafter is data, right? So again, these are present in essentially every wireless communication scheme. We're basically just going to write software to look for these things to synchronize our receiver to the transmitter and start framing our data out. Finally, step 5 is to extract the symbols. And that's to demap the modulated symbol values back into their digital values. Exactly what this process looks like depends on the modulation that we're using, but we're going to illustrate this with some examples in just a moment. So here's our methodology. And to illustrate this, we're going to go through 3 examples. But before we do, my colleague Marc is going to talk a little bit more about open source intelligence and how it can be leveraged to make this process quite a bit easier.
So I'm a big fan of open source intelligence, and especially applying it to these kind of problems. And the reason is that it enables us to be lazy and offload the work to documentation that we can publicly find. So if you're going to sell a device with a radio transmitter, in most markets it has to go through some type of regulatory certification. In the US, we have the FCC, IC in Canada, CE here in Europe, and each organization has the same purpose of evaluating a device to determine does it fit certain constraints for that certain market. So that would be what frequency does it operate on, what is the transmit power, the channel bandwidth, does it hop around, what is the duty cycle. And the purpose is to, again, meet these regulatory constraints. With the FCC in the United States, it's quite handy because it has a very verbose amount of information for each device. So if you're selling a device in the US, you send it to a test lab, the test lab operates the device, and the test lab will put together a test report with a lot of physical layer information about how the device operates. So if you're looking at a device which is sold in the US market or sold in the US plus other markets, you can look up the device on the FCC website, pull down this test report, and that will tell you oftentimes the modulation and all the channel characterization you need to know about the device. If it's not an FCC certified device, you can look for technical documentation. So often it's easier for a manufacturer to use an off-the-shelf transceiver than to roll their own. So you might have transceivers from Nordic or TI or ADI or CC or one of these RFIC vendors. So you can either look inside the device or find internal photos somewhere online and look up data sheets for the transceiver that's in the device. That will often tell you all the physical layer characteristics, sometimes packet formats and protocol information and so forth. There's also patent filings are pretty useful. And if you're interested in more information on kind of the granularity of applying this OSINT to RF reverse engineering, I gave a talk about this here last year, which is up on YouTube.
Okay, so we're basically going to insert open source intelligence research as step 0 to this RF reverse engineering workflow that we're going to follow. The reason why is because by doing it first, we're going to show that we're going to be able to skip or drastically shorten the discovery process for some of these later steps. All right, so now let's get into some examples. First, we're going to look at this wireless camera flash trigger. It's made by a Chinese manufacturer named Yongnuo, and essentially this device fits into the hot shoe of a DSLR, and it translates the signal that would instead set off a camera flash into a wireless signal that can be received by a wireless-enabled flash. And the reason why you might want this is if you're a professional photographer and you want to get just the right lighting, you can set up a number of flashes around your subject and get more control. Again, we don't really care what the device is in this case. It's just an example of the sort of thing that you might find in one of these low-complexity IoT protocols. So let's reverse engineer this thing and see how it works. So again, starting with step 0, we're going to do some open source intelligence research. Now, immediately we ran into a bit of a hurdle with this, and that's because the FCC ID is not silk-screened on the device. Oftentimes when you're looking at wireless devices, the FCC ID will be printed on the enclosure. It's a regulatory requirement for devices in certain classes, and interestingly enough, this device did not have that. However, Marc's favorite Google dork was very, very helpful here. If you Google site:/fccid.io followed by the model number, it will almost always return the FCC ID. So that was very helpful here. So this gleaned the test report. And looking into this device's FCC test report, if we look at the equipment under test section, we're immediately greeted with some information about the channel and the modulation. So here we see it's a 2.4 gigahertz protocol, and there are 16 channels defined. And it also tells us that the modulation type is frequency shift keying. If we keep digging through the report, we find a detailed channel mapping showing exactly what the center frequency of those 16 channels are. So by doing some open source intelligence research, again, just quick Google search and reading a document, we're able to determine that there are 16 channels, identify what their center frequencies are, and also determine the modulation type. And that's without even looking at the radio, right? That's just having the device, doing a Google search, getting some information. So open source intelligence really starts the process and gets us on our way here. So one thing that we were not able to recover in this process, the last step in characterizing the channel, is the bandwidth, right? So we can measure this empirically using our software-defined radio and our device. So if we generate some traffic with the device, we can use any number of tools to measure the bandwidth here. You can use Baudline and Spectrum are two that I really like. They're both spectrum visualization tools. You basically can just load up your capture and then use the cursors built into both to measure the width of the channel. And then we can discover the channel is 500 kilohertz wide. So having discovered that, we've now fully characterized the channel and have identified the modulation. So steps 1 and 2 are done. So another element that we weren't able to recover through open source intelligence, open source research, is the symbol rate. But that's okay, because that's another thing that we can discover empirically. So to discover the symbol rate empirically, I like to use Spectrum again, because Spectrum has a really useful tool called cursors. Basically, you can break out a generic FSK or on-off keying demodulator, and it will produce this nice time series visualization of the data there. And then you can use these cursors to very precisely clock out exactly where the symbols are. So you basically just align the cursors to your time series data, and it will tell you what the symbol rate is. So here we're able to discover that the symbol rate is additionally 500 kilohertz. So with that, we've completed step 3 as well. So at this point, we've characterized most of the critical file elements here that we need to be able to translate what's happening in the wireless domain into bits on a disk. So we're going to take these first elements and turn them into a GNU radio flow graph. It's going to produce a stream of symbols coming from our software-defined radio. And again, so this flow graph that we're going to put together is essentially going to capture raw radio information using the SDR, do some math on it, and it's just going to give us a stream of 1s and 0s. Once we have the 1s and 0s on our system, on a disk, we can parse through them using any tools we desire, right? You can use any language, any workflow you want, because it's just a binary format, just like any other data. So we're going to implement that with Python, because Python's really easy. So beginning with the flow graph, came up with this here. It looks horrifying. I'll walk you through it. And this is actually something that's fairly generic. So we're going to release this online, and you're going to be able to take this, and just by modifying the variables on the left-hand side of the screen there with the values that you'll find through open source intelligence for whatever protocol or device you're researching, we'll be able to use the same flow graph to demodulate FSK signals. And you won't have to touch the blocks, you'll just have to touch the variables on the left-hand side. So it's a lot less scary than it looks. So the first oval on top is essentially establishing our channel. The rotator is centering our signal at the middle of the channel that we're looking at. The resampler is essentially throwing out anything that's outside of the channel, and then the low-pass filter is just cleaning up any spurious stuff that might be left over. The second oval, the oval on the left there, bottom left, is the demodulation. And quadrilateral demodulation is a means of doing FSK demod. It has that scary floating point gain value in there, but that's auto-populated in GNU Radio, and it's just taking the values that we're providing in the variables. So, no knowledge or math required there, just being able to Google some stuff and plug some numbers in. And finally, on the right, we have clock recovery. And that's essentially doing the translation between the sampling rate that our radio is capturing radio information at to the symbol rate that we expect on the demodulated side, that we expect the demodulated data to be at. And again, most of the values here are the GNU Radio defaults. There's actually a lot that can go into tuning clock recovery to make it work well. But if you don't want to go through all that, one way that you can kind of get around that is to oversample. That's a way to make get around some of the nuances there. So that's kind of a walkthrough about what's happening here. And then finally, after clock recovery, we're basically just dumping the ones and zeros to a named pipe, in our Linux system, so that we can ingest that into some other piece of software to parse through it. Okay, so essentially steps 1 through 3 were baked into that flow graph. And steps 4 and 5 we're going to do using a Python script. And the Python script is actually pretty simple. Really what it's doing is it's looking at the stream of ones and zeros that are coming in from the GNU Radio flow graph. And it's looking for the preamble. And the preamble is going to be that alternating sequence of one-valued and zero-valued samples, right? Because with FSK, the preamble we expect is going to jump back and forth between the two frequencies, just as we saw in the interactive example. So once we see that alternating pattern and our state machine establishes that we're about to receive a packet, we start to look for the start of frame delimiter so that we can synchronize. And the start of frame delimiter in this case is empirically observed to be 2 zero-valued symbols. So basically, the transmitter sends its preamble, and then at the end of the preamble, it just sends another zero value. It sends an extra zero value symbol to tell the receiver, hey, the preamble's done. What follows immediately after the second zero-valued symbol is your data. So once we're synchronized, we're going to read out the frame just by using some arbitrarily large MTU size. So once we're synchronized, we're just going to dump out the next, say, couple hundred bits. And then we can parse through that and try to make sense of what's actually happening here. So the application layer in this case actually turned out to be fairly straightforward. Essentially, this wireless flash trigger has a single broadcast command that will cause every camera flash on this channel to fire, to engage. And then these flashes can be remotely configured by using a series of 5 commands. However, only the 4th command carries the state information. The other ones are always static no matter what you're trying to do. And I think they're probably like wake up and synchronization messages or something like that. It actually doesn't work unless you send those as well. So by using this series of configuration commands, you can update a single flash group's settings. So you can basically change the mode, whether it's on or off, and change the flash power and some things like that. So do a live demo here, see how it goes. So just to show you what this looks like, wake up my flashes here, they've turned off. And there you go, so those are live flashes. And I'm going to fire up my my demodulation flow graph just to show you what it looks like to receive these packets over the air. So on the right is the GNU Radio flow graph that I just showed you the picture of. That's running on the right-hand pane. And then on the left is a Python flow graph, or is a Python program that's going to dump out the ones and zeros that follow after synchronization. So this Python script is basically finding the preamble, then synchronizing against the start of frame delimiter, and it's just going to print whatever follows. And because it's 2.4 gigahertz, we might get some interference and some false detections and things like that. But basically, as I modify settings on the camera, we see all sorts of information getting dumped out. So, these are just, ones and zeros. You can basically change the state on this and correlate it to behavior in the packets. And since we're kind of leaving it up to you, we're assuming that you are familiar enough with binary formats that you can work through that once you've translated the radio information into a format like this. So now we're just going to do a quick little transmission demo. So basically both flashes are configured to be on right now. They're both enabled to fire. So if I start up my transmission GNU radio flow graph here on the right, I have another script that will go and compose. It's basically going to compose the formats that the flashes expect to get them to fire. So if I fire this up, they'll fire as well. And this is a little bit buggier, but we're going to try it anyway. I'm going to try turning off the A group flash, which is the red flash here, and firing the blue one. And I'm going to do it using the remote configuration commands here. Let me try this one more time.
Maybe the red one was already off. I'm not sure if it flashed before.
Let's try it again. It should definitely be on.
Now they're both.
Yep, so they're both on. Let's try turning off the second one. And this is how you know it's a live demo. Okay, there we go. So I've just turned off the B group. And now I'm going to fire it again. And instead, you should only see the red flash go off here, which is the A group flash.
Yep.
Oh, that's right. Thank you. Operator error. There we go. So now only the A group flash is going off. Cool. So that's the process. I know we kind of went through this at a high level, but essentially that's the process that I went through in order to go from having this unknown wireless protocol to being able to interact with it using a software-defined radio. So just before I hand it off to Marc, I want to show off a little bit of extra content. Given that I was sitting at a desk by myself and hitting the shutter on this camera a bunch of times to produce lots of traffic, I came up with some fun pictures. So. Here is a tour of the east-facing wall of my bedroom. You can see my IKEA lamp out of focus. Here's the southeast corner of my bedroom as well. Some nice still life of my apartment here. A self-portrait, and some more still life. So now I'm going to hand it up to Marc, and he's going to take you through another wireless device.
So now let's look at another device here. In this case, this is a wirelessly controlled LED strip. So it's just you plug it into a USB port. It has a little radio receiver right here. You press a button on the remote, and then it operates the LED strip. So for example, I can plug this in, hit the remote, and it turns on and off. And this is operating over RF. So this is a kind of unknown device. I ordered this online. It doesn't have any markings in terms of a model number or a vendor number. So I don't really have much to go on in terms of open source intelligence, no FCC ID. However, we can do a little bit with the user manual that we have. So this is the front page of the user manual that came with this, and there is nothing useful there. We can flip it over. There's some more words. Some of the words are interesting. We can see here we have a 433.92 megahertz center frequency. So this gives us some information about the channel that the device is operating in. So through this very minimal amount of open source intelligence, the only stuff we could actually do, we're able to characterize the channel and get the center frequency that this device operates at. Now, in order to start looking at the modulation and to fully characterize the channel, we're going to visually look at the signal in a spectrogram. So this is a very, very simple GNU radio flow graph. We have a USRP source on the left. This is data coming in from the software-defined radio. Then we have a baud line sink on the right. And this is just displaying this spectrogram like we see on that image there on the right. So this is one full capture of a packet. It's a little bit small, so we're going to zoom in to take a closer look. So this is a zoomed-in view of the first half of one of the packets sent by this LED remote. So we can start to see that something is happening here. We have starts there with the transmitter being on, then the transmitter off, transmitter on, transmitter off. And so we can start to see that there's some pattern happening here. And we can see that there are two different states that we see. So first we have that top example of the transmitter being on for around 450 microseconds and then turning off for around 1200 microseconds. And then we also have the inverse of that, where the transmitter is on for 1200 microseconds and then off for around 450. And so we can see that we have these two distinct things that are repeated. So we can infer that one of these is going to be a 0 and one will be a 1. So we can, in this case, visually demodulate the signal and just say 0, 0, 1, 1, 1, 1, 0, 1, 1, 1. And some of these simple physical layer protocols, you can actually do this visual demodulation and not have to even write any code. So this is what's called pulse width modulation. And it's a type of on-off keying where the data is encoded in the duration of the time that the radio transmitter is on. So when the radio transmitter is on for 450 microseconds, that's a bit 0. When it's on for 1200 microseconds, that's a bit 1. And this is just a nice, simple, low-complexity IoT PHY. So now with a little bit of visual analysis, we've been able to get the modulation and the symbol rate. So we have a 1650 microsecond duration, and that's because we have 450 plus 1200. So that works out to be around 600 bits per second data rate. So now we need to synchronize. We have these bits described and modulated that we can see, but we don't know what a packet actually looks like. And so I pressed some different buttons on the doorbell, 4 different buttons, or on the LED remote in this case. So the first 20 bits of each packet is the same. So I'm making an assumption here that the first 4 bits are going to be some kind of synchronization field, and the next 16 will be an address. This is kind of an unknown, so it's logically separated like this for the moment, but we need to get another remote to see where the address actually starts. The last bit in each packet is always the same, so I'm assuming that's maybe a trailer of some kind. And then the 4 bits that precede the trailer change depending on what button I press. So this tells us that the button ID is encoded in those 4 bits before the trailer in the packet.
I think that was one of the flashes running out of battery. So
good.
The,
So this is what our, in bits, this is what our packet format looks like for the LED controller. So we have a sync field and an address. The length of each are unknown, but we can assume these for the moment. Then we have a 4-bit ID for the actual button on the remote, and then this 1-bit trailer. And another thing that we have to consider is the packet spacing. So when you hold down a button on the remote, it sends these same packets over and over again. So it'll send a packet, wait 12 milliseconds, and then send the packet again. And it will just keep doing this as long as you hold down the button. The reason is that there's no way for the LED strip itself to reply to the remote. So in order to make sure that the commands are received, it just spams them continuously. And so with a tiny bit of open source intelligence and a little bit of looking at a spectrogram, we've been able to learn quite a bit about how this device operates. We know it's a 433.92 megahertz center frequency, so we've characterized the channel. We know the modulation is pulse width modulation at 600 bits a second. We know how a bit 1 and bit 0 are modulated. We know the packets are 25 bits long, and we know there's a 12-bit spacing between each packet. And this is enough information to write a little bit of Python code to actually interact with this device. And when you're doing this GNU Radio stuff, a lot of people will like to use a GNU Radio Companion software, which is perfectly fine. But when you compile a GNU Radio Companion flow graph, it just produces Python code. So I prefer to just write the Python code. And in this nice low complexity case, it's not too much code.
Can you increase your font size?
Yes. So we start here with our USRP source, and this is just data coming in from the software-defined radio. We pass that through a low-pass filter, which filters out everything outside of the signal we're looking at. Then we have this block called complex to power here. And this is taking the power of the signal on the channel where the LED remote is operating. So what happens is this is telling us the power of the radio that this thing is transmitting. We then have a threshold block. The threshold block will output 1s or 0s if the power is above or below a certain threshold. Right? And so the data is encoded, modulated, by turning the radio transmitter on or off, and then on, and then off. And so this will output 0s when it's off and 1s when it's on. We can then look in those 1s and 0s for the packets. We then go into a framer block, which will actually try and frame the packets here. So we have the output of that threshold block, which is just setting our 1s and 0s, telling us if this is transmitting or not. We look for the state change of going from off to on and then off. And when it goes back to off, we see how long it was. So here we're saying if it was on for less than 500 microseconds, we call it a bit 0. If it was on for more than 500 microseconds, we call it a bit 1. And then when we have 25 bits, we call it a frame. and then we extract the button ID and we print the command to standard out. So I can go over here and do a quick demo of this. So now I can press some buttons on the remote, and we can see that it is operating the device and then telling us what button was pressed. And now the inverse of this for a transmitter is another pretty simple piece of software here. So we, again, for the transmitter side, we have a signal source, and this is just generating a tone that we send into the software-defined radio. So as it is with a signal source going into the SDR, we're going to have a tone that's always on at a 100% duty cycle. But in order to modulate this data, we need to turn this tone off and then on and then back off. And the easiest way to do that is multiply it by a bunch of zeros when we want it off, and multiply it by some ones when we want it on. So we know that the bit 0 is modulated by having the transmitter on for 450 microseconds and then off for 1200. So we generate a mask for this bit 0. And this mask is just 450 microseconds of ones and 1200 microseconds of zeros. And then we have the inverse of that for bit 1. And then we can build our packet here as just a string of ones and zeros. And then we can make a packet mask, which is just concatenating these bit 0 and bit 1 masks, so ones and zeros in this big vector that we can then multiply by the tone to turn it on or off to modulate this data. And then we build in our 12 millisecond gap between packets, and then we can transmit a few instances of this. And the idea is that the LED strip here will receive that command and then do things. So go and demonstrate this here. So first I will send the power button command, and that will turn it on. And then we can, for example, change the color. And then run power again and turn it back off. This is kind of a neat example of low complexity on-off keying, because we have maybe 100 lines of code for the receiver, 100 lines of code for the transmitter, and we can effectively communicate with the device. And so now let's take a look at another device, in this case a wireless keyboard. So this is the Hewlett-Packard Classic Wireless Desktop. This has 3 devices in this set. It's a keyboard and mouse set. It has a keyboard, a dongle, and a mouse. We're just going to look at the keyboard and the dongle in this case. And what's nice is because each of these devices transmit, it's from a major vendor sold in the US, so we have FCC IDs for each of the devices. So we can start by pulling up the test report for the dongle. In this case, this tells us the modulation, which is GFSK modulation, the data rate of 1 megabit per second. This tells us we have 78 channels in the 2.4 ISM band. So right there we have the modulation and we have the channel characterized. We can also pull up the test report for the keyboard. Now in this case, we have a little bit of conflicting information. So we still see FSK modulation, but this tells us a 2 megahertz channel bandwidth, which is compatible with a 1 megabit data rate, but can provide some ambiguity. But the big problem is it says 34 channels, whereas the dongle said 78 channels. But we can at least say that it's going to be a 1 megabit data rate, it's going to be in the 2.4 ISM band, and it's going to be FSK modulation. And because this is a device that can talk to a computer, we can plug the dongle into a computer, look at the D message output. In this case, it identifies itself as a Mozart semiconductor device, and it turns out that's just the vendor which makes the transceivers in this set. So the first thing we want to do is figure out what these devices actually send over the air. And so because we have 2 transmitters, we have the keyboard and the dongle, we can start by plugging in the dongle, pulling up a spectrogram, and trying to see what's happening. So it turns out that it actually camps on a single channel, so it's not hopping, and it's only one channel. So the differing channel numbers in the SEC documentation is now irrelevant. And we can see that when just the dongle is plugged in, it's transmitting these packets every 8 milliseconds. So this infers that it's probably going to be some type of time division multiple access. And so instead of having 2 devices operate on 2 different frequencies, you can have 2 devices operate on the same frequency, but at different points in time. So now we can plug in a keyboard, type on the keyboard, and we can see that this TDMA is indeed there. So we have the dongle still sending packets every 8 milliseconds, and the keyboard, when you're typing, will send a packet shortly after the dongle packets. So this tells us that we have a TDMA PHY, TDMA FSK PHY, and it's a single channel, so no frequency hopping.
Excuse me.
Yes?
Can you explain about the dongle? The dongle is not transmitting anything, is it?
So the dongle, it's not transmitting any data, but it's transmitting these synchronization packets. So the idea is that the keyboard will then listen to those, and it will know that when I see these packets, then shortly after that, I'll transmit my packets. Then if you were to move the mouse would be another 2 milliseconds after the keyboard packets. So it allows you to have 3 devices sharing the same physical frequency channel.
Keyboards do have LEDs normally that can be turned on and off, so it's not always one.
Right, yeah, for caps lock and such, yeah. So now that we know that these devices are transmitting on a single channel, we know the modulation type, we can start to demodulate the data and see what bits we get out. And the problem is, because we only really care about what the keyboard is transmitting, we first need to figure out what the dongle is transmitting so we can ignore that. So this is a simple GFSK demodulator flow graph. So we start with our USRP source, getting data in from the SDR. We go through a low-pass filter to filter out anything outside of the channel we're looking at. We run it through the GFSK demodulator block, and this block just turns radio waves into bits that we can play with, and then we write those to a file on disk. And I'm a big fan of using just common Linux command line tools for parsing these files and looking for packets. And as we learned earlier, a preamble is usually alternating ones or zeros. Sometimes it could be all ones or sometimes all zeros. So we can send this demodulated data that was output from GNU Radio through the XXD command. This will give us a standard outprint of the hex characters representing the bytes in that file. And because alternating ones or zeros are either the hex character A or 5, and all ones or all zeros are either FF or 00, we can just grep for those hex characters, where we would find the preamble, and then we can look for the next 8 characters after that, which would be 4 bytes. That's a reasonable length for an address. And then we can just see what's repeated over and over again in the output file and sort by the unique counts. And we run this command, and we, the bytes count, sort by count, we get this output here. And this is going to be the packets that are transmitted by the dongle. So we have 4 Fs, a bunch of As, and then 4 bytes. So that's going to be a long preamble, and then 4 bytes, which are going to be either an address, or at least the first 4 bytes that the dongle is transmitting. And this is pretty great, because then we can do another capture with the keyboard and dongle. We can use sed to just replace the dongle packets from the dongle plus keyboard packets, and then we have a file that has presumably only the packets that are sent by the keyboard. So we can run that grep command again, and now we have something different. We have a shorter preamble, and then we have slightly different address bytes, or first 4 bytes of the frame, that the keyboard is sending. So then we can take this sequence, we can grep for this sequence plus some additional bytes, and find the longest repeating sequences we see, and that's going to likely be what the keyboard is sending. So we do this, and we have this set of packets which are repeated a bunch of times in the file. And now we can use our normal packet format analysis skills to figure out what's in here. So we start with the preamble, an address, a sequence number, a frame type. In this case, it means a key press. We then have a keystroke, which is the actual key being typed, and we have a 16-bit CRC. Now, what's kind of fun here is we've barely touched a radio. We can say we haven't written any code outside of dragging and dropping some stuff onto a GNU radio flow graph, and it's allowed us to go from knowing nothing about the device to knowing exactly what the packet format is that it sends over the air. And this is because people much smarter than me have built out this great ecosystem of tools to make it possible to leverage open source intelligence and these open source tools to really get away from all the radio stuff and treat it like a normal software reversing problem.
Okay, so let's draw some conclusions and tie this all up. So we proposed this reverse engineering methodology that we've shown can be applied to a number of wireless PHYs to make the process of reverse engineering them quite a bit simpler. So we've established that all 3 of these PHYs share this common notion of a channel. Whether it was on-off keying, pulse width modulation, or FSK, they all occupy some predefined amount of spectrum that can be characterized. They all use some type of modulation, and this is the biggest variable, but by relying on open source intelligence, we can make the process of discovering it easy. All 3 PHYs share this common notion of discrete symbol timing. And again, we can rely on open source intelligence to discover that as well, and when that fails, we can discover it empirically. All 3 PHYs contain synchronization features, being a preamble and a start of frame delimiter. And although they look different, for each different PHY, they're all there. You know what to look for, and then you can leverage them all the same way to aid in the process of framing and decoding your data. And then once you get to step 5, extracting the symbols, you have bits on a disk, right? And since you're here at Hack in the Box, you probably have these skills. So you can apply the skills that you have, traditional software and network analysis skills, to these wireless protocols by leveraging this open source intelligence and all these tools to make the process of going from RF to a well-understood protocol quite a bit easier. So we've shown that we're able to apply the same process across these 3 different PHYs to make the process of reverse engineering these protocols quite a bit easier. So to wrap up, these disparate wireless systems can be rationalized and understood by applying process to them. Additionally, open source intelligence will help you bypass the really brainy radio and complex domain-specific parts of the problem. You can rely on existing tools and public information to make that easy. And then once you've demodulated, you have bits on a disk that you can parse through using any mechanism that you please. And one last thought that we want to leave you with. As we know, the Internet of Things is full of holes. And it's up to you guys to find them, right? The only way that IoT security is going to get better is if we start to look more critically at these different systems and protocols and find out how they're weak so that we can start making them better. So with that, thank you for your attention, and we'll be happy to take your questions with the time that we have left.
Thank you, Matt and Mark. So here's first question number 1.
Hi. So recently there was a piece of software release called Universal Radio Hacker. What's your opinion on that? Because it claims to put all this process under one single piece of software.
I haven't had an opportunity to play with it yet, unfortunately.
Can you repeat the name one more time?
Universal Radio Hacker. It's under a project called URH on GitHub.
Okay, I'll have to take a look at it.
Sure.
I know there's been some open source research on doing automatic demodulation. I know there was a paper that came out of I think GNU Radio conference a year or two ago that was using, I think, neural nets to do automatic modulation recognition. And then I know at ShmooCon there was a tool that was released that would have made the process of doing automatic demodulation of FSK and on-off keying signals quite a bit easier. I haven't played with any of the real modern tools that have come out, but I know that some of the early attempts at it were not super reliable.
I have not worked with URH either, but from what I can understand, it's not automatic either. It's just it's like in Spectrum, but you can demodulate manually, and it shows you the bit stream individually. So
okay,
yeah.
Cool. We'll have to take a look.
Thank you for your talk. One moment in your methodology that might not be clear to everybody. So between the modulation or demodulation and the actual bytes, normally there also is an encoding or decoding. So how do you find that in a wireless protocol? When you have a wired protocol, it's sort of okay. We know that there's like Manchester encoding. We know like low level of signal is 0 and high 1, or vice versa. How do you do that in wireless?
Yeah, so that's a great question. So you can apply similar methods that you might apply to recognizing them on a wire to wireless. And there are two examples that I'll point to if you want to do some further reading on this. We just gave another variant of this talk at Troopers about 3 weeks ago. And we showed off completely, the first 20 minutes were approximately the same, but all the demos were different. We looked at different devices, different PHYs. And one of the devices that we looked at was a Manchester encoded FSK signal. So, what was the critical thing that clued us off to it being Manchester encoded was a discrepancy between what we were observing over the air versus what was in the test report. So you might want to go take a look at the video from that talk, and we go through it in a little more detail. Obviously, that's a fairly straightforward encoding example. There are other protocols that use quite a bit more encoding. For example, LoRa. The encoding on that was fairly involved. And it involves, I'd say working through it really just involves using the open source knowledge you have, open source information you have, and just really structuring your iteration through all the different permutations that it could be. So, hope that addresses your question.
Okay, last question over here, and then we've got to go to the next speaker.
It's not questions, as remarked that when you record something, you can also, often on GNU Radio, IRC, you can post just your capture and people will be very helpful saying, oh, this is FSK or this, I recognize this. So the internet is also a great source for for that.
Great community around this kind of stuff for sure.
Yeah, there's a lot of collaboration, as you say.
Okay, thanks again, Mark and Matt. If you've seen it, their email addresses are on somewhere at the bottom of this last slide. You can, of course, find all the slides on the Hack in the Box website, so they will be updated later. So that's it.
Okay, thank you.